Welcome everyone. Today is the last session of our webinar. So before going to the session, I just want to give a quick reminder that please mute yourself and turn off your video during the session. Now I'd like to request Abhishek sir to introduce Mr. Vishal Das with us. So over to you.
Thank you, Madhumita. Like all good things have to come to an end. This first webinar series that we started on Monday draws to a conclusion with the ninth and the last presentation. And who better to do it than a very close friend and junior of mine who graduated from the Department of Geophysics in 2012. I have the pleasure to introduce Vishal Das. He's a geoscientist who currently is also a colleague of mine at Shell, working in deepwater development Gulf of Mexico team based in Houston. After he graduated from ISM in 2012, he went on to have another master's degree from Stanford in geophysics before going on to do his research at the same university on numerical modeling and deep learning of seismic reservoir characterization. Now, this is where the topic of the day, this ninth topic, the way we have structured it as digital enablers, data-driven methods in geophysics, is very intriguing. Intriguing because words like machine learning, deep learning, they're no longer buzzwords. A couple of years ago, they were buzzwords, but if you go beyond the hype, they are actually now being tasked to do a lot of things. Predicting an output, identifying objects, moving physically or simulation, uncovering trends, you name it. There are so many areas they are now being applied. So just to listen to Vishal when he talks about various deep learning methods and when he delves into convolution neural networks, I am really looking forward to it. And I suggest everyone who dials in to the session today, my request would be to stay till the end and listen to it. There will surely be enough things to take away from what you are about to hear. So, Vishal, over to you.
Thank you so much, Abhishek. Am I coming in loud and clear?
Yes, sir. Sir, you are.
Okay, good. So, well, thank you guys for having me over. I know this is a Sunday evening. I mean, I'll try to make it a little bit of fun for you guys so that, it's not just another boring presentation or a lecture. And thank you, Abhishek, again for your introductions and also giving me the opportunity to be part of this. So without much ado, I'll start off with the presentation. I have quite a bit to cover. I mean, this is a field which is growing very, very fast. So, I mean, as we speak, probably there is a new method that's coming up somewhere, or something new and exciting is happening in this field. So it's a pretty vast field, but I'll try to delve into it from the basic first principles and really give you guys a very high level introduction, and we can then take some questions towards the end. I do have a plan to do a very quick demo of how we could use some of the tools to do this digital analysis, but it's part of my high ambitious plans. So we'll see how the presentation goes and how we do with time. So as I speak into this, or to be honest, when I talk about any research topic or any business problem, I have my agenda based on the three main questions. So the first thing is, why are we doing this? Once I try to satisfy myself with the answer that yeah, it's important enough to be done, and like Abhishek already mentioned to us, it is important and it's no longer a buzzword. Then we go on to how do we do it, and then finally what do we get out of this? So this is going to be the theme of my presentation today, and I'll first start off with why do we do it. And I hope some of you guys remember this uh, plot or diagram. It's a very simple Venn diagram. I showed this during my last presentation as well, and in fact I show it everywhere. Right from presentations here in Shell, or if I have to go into conferences, or or any other place. So this is where the crux of the whole why question comes in. So why do we do data analytics? So this is what Bergen et al. 2019 they described this in the very basic high level paper on how to use deep learning, machine learning, and data analytics for geosciences, and they mentioned something which is very appealing. So this is what we call the universe of the whole function space. That's the big circle at the outer periphery. So that's like all the function space that defines the data and its prediction relationship, right? So, and it's a huge function space, and we can possibly never ever see the whole function space by itself. So it's practically impossible to have all possible functions that define the data and the predictions. But we can aspire to be, to have a good enough vision of what is there in the function space, and on the most inner part of this whole Venn diagram, you can see the red dot here. So that's what we call the domain specific classes of functions. So what it means is that all the functions that comes out of these domain knowledge, physics based knowledge, and stuffs like that, so those come into the middle. So they form a very tiny aspect of this whole function space, and that's because we do a lot of approximations. So what really data analytics and machine learning helps you to get as an added advantage from the domain specific classes of functions is an extra. They do span a very small space of this whole function space. So that's why we should use data analytics, and that's why we are seeing that data analytics and data driven methods give us some extra value which we would possibly not get from the physics driven methods. So, all right. So I hope I did make my point on why you should do data analytics, and I'm sure Shubhro Roy, when he presented his presentation, he must also have made the point about digital oil fields and stuffs like that that's going on, and it's quite coming up in the industry. So the question that is often asked when we do data analytics, and then when we do all these data driven methods, is how do we do data analytics? So there are a bunch of statistical methods, and these are not very new. Some of them are pretty old, but I've tried to list down some of the different varieties of the data analytics method. So it really comes from a Bayesian classification, for example, where you try to formulate a problem in a probabilistic sense and try to get predictions out of an observed data. You have things like discriminant analysis, where you try to discriminate the data based on their variance, or how much they differ from each other, and then try to classify different clusters of data. So that's in there. You do have things like artificial neural networks that have like simple neurons that are pulled together in different layers, and then you pass an input through the different layers and try to get a prediction out of it. And then of course you have the modern deep learning methods, and one of the most popular one is the convolutional neural network. So these are some of the ways that we do data analytics. And if you really go into history, and if you really try to see when all of these originated, so they did come into picture a long time back. So the first paper on neural networks and neurons and using them for computations came way back in 1943. So that was way before most of us were born, right? I mean, probably everybody who is right now very active in the industry or in the academia in this space were, you know, not even born at that time. So it's way back. Like the history goes way back. So it's a paper by Pitts and McCullough, and they describe the way, like, you know, the neurons in the brain can be emulated in a mathematical formulation and used for computations. And then came Rosenblatt, and he introduced the concept of perceptron, and that's, like, you know, stuck around for a while. We still see artificial neural network ANNs which use the fundamental building block, which is called perceptron. And then we had papers from Fukushima, and then LeCun is still active now, right? So he's heading the Facebook research team, and they came up with this idea of convolutional neural networks and deep neural networks and stuffs like that. So yeah, so it has been around for a while, and like I was mentioning before, the idea of perceptron that Rosenblatt described way back is basically the building block for a lot of these artificial neural network techniques. And let me actually describe that to you. And this is like a very simple slide that Professor Tapan Mukherjee uses in some of his presentations, and I borrowed it from him. So essentially, what happens here is that you have one neuron, single neuron, which we call as the perceptron, which is sitting right in the middle of this slide, and that is essentially a combination of weights that you know are applied to the input data, which is all the x1 to xd in here, and you add a bias term to it. So what essentially it is doing is it's doing a weighted averaging of the input data. So and after it does that, what happens next is that it passes it to a non-linearity. So it's almost like a non-linear regression. So in this case, for example, a non-linear function can be what is called a rectified linear unit, so ReLU. So essentially it's nothing but a function that truncates all the values and make them, like, you know, positive. So anything below 0 is 0, and anything above 0 is the number by itself. So that's a non-linearity. You can have other non-linear functions. For example, this is what we call tan h function. There are other functions like sigmoid function, and essentially the output that you get from all of this is a non-linear weighted average of your input data. So that is what is described here. Y is a function of the non-linear function, which is applied on the weighted average of the input and a bias term added to it. Right. So this is essentially what we say is the basic fundamental building block of some of the artificial neural networks. Now, if you take that one perceptron and line them like in a series in one layer, you get what is called an artificial neural network. So essentially, previously you had all the x's, which are the input data, going into one perceptron. Now you have them going into multiple perceptrons, and then they pass through the nonlinear function and give you the output. Right? So that's what we call a single layer of multiple neurons. Now, if you have multiple layers of this multiple neurons, you get what we start calling as a deep neural network, right? So the depth of the neural network really depends on the number of layers that's inside the network. And again, from a fundamental fundamental point of view, what is happening is still the same. It's a weighted averaging. Instead of having a one neuron or a one layer of neuron, it's passing through several layers, and what you get out of it is essentially a function of the weighted average of the inputs passed through the different nonlinearities. And this is essentially a nonlinear function of inputs, which is parameterized by the weights of of the layers. And and you must have heard a lot about training a network. So what we are essentially doing is basically we are trying to optimize for these weights. So we do not know the weights, we try to optimize for them, and that is done often through what we call as stochastic gradient descent method. And there is a lot of detail in here where we why we use stochastic gradient detail. So I'll leave it on you guys to pursue on your own time and space. But essentially what we are trying to do here is that we are trying to define a loss function, which is essentially a loss between what you expect and what you predict, and you're trying to minimize that as much as possible. So you're trying to go as close as possible to your expected value. And in order to do that, the levers that you can really play with are these weights. So you're trying to optimize and find values of these weights through some kind of an optimization function. So I'll leave it at that. All right. So now coming to the two distinct categories of all these machine learning problems, we have two distinct categories. So it depends on what is the output that you're trying to predict, and there can be some hybrids of this that people are starting to work on, realized that you can actually combine some of these things together. But essentially the two broad categories of all these problems come into the type of the variable that you're trying to predict. So if your variable that you're trying to predict, which is y in this case, is a continuous variable, then it is what we call as a regression problem, and in this case a nonlinear regression, because we are going through all these non-linearities. And in this case it's essentially the objective function that we try to optimize for, and there can be different variations of this, but this is like a basic objective function that is often used is essentially the least square error. So what you're doing is you're trying to find the difference between the predicted variable, continuous variable, and the observed value, and you're trying to minimize that error in a least square sense, right? And that's what is done in linear regression as well, although the mathematics and the statistics behind that is very well established. The other category of variable is actually categorical variables. So where you have, instead of a continuous variable, instead of having values which are continuous, you have discrete values. So you might have like values like 0, 1, 2, 3, and this might represent different things, right? So for example, in geophysical problems, so you can have different logs, well logs. You've seen well logging in some of our previous lectures. So you can try to identify the facies from there, right? And these are discrete classes. So facies would be either sand or shale or silty sand, sandy shale, or things like that. So you can have them as different values, 0, 1, 2, and 3. And in this case, what you're trying to do is to, optimize for the misclassification. So you're trying to classify uh, or predict the classes, and then you're trying to optimize for the misclassification. And there are different objective functions for that. Just as a pointer, there is a very popular one called the cross entropy or cross entropy softmax error. So those things come into place when you're trying to do a categorical classification problem. All right, so that was the basic building block for the neural networks and things that happen in that space. Now coming into some of the modern ones, right? So one of the popular ones, and it became popular mainly from the tech industry, right? Mainly from advertisements and stuffs like that, is the convolutional neural network. So again, here it's the same concept, right? There's nothing different in here. Only that the only thing that's different in the convolutional neural network is the type of neuron that you're using, right? So instead of using Rosenberg's perceptron, what you're trying to use now is a convolution filter, and this convolution filter can have different sizes. There can be 1D convolutional filters, there can be 2D, there can be 3D, or even more higher dimensions, right? So again, it's a cascaded like layer of these neurons, which in this case is a convolutional filter, and you have the weighted averaging using these filters, right? So and you will see that there are some very standard terminologies that's starting to pick up, and people start to relate to them. So for example, we have what is called the non-linearities through ReLU, and I did touch upon ReLU. So that's a rectified linear unit, right? The function where it truncates everything below 0 to 0, and everything else it keeps the same. Then you have things like pooling, subsampling, where you try to pool the data together, or you sometimes do the opposite, upsampling as well. There are various sophistications of this, and essentially what it is doing is it's again passing the inputs through the neurons, and applying a lot of this fancy non-linearities to them. And one of them, which I'm showing here, is a very popular one. It's called Alexnet. If you haven't heard about it, you should try googling for it. You will see that it's actually a very interesting one. It's one of the most popular ones that really showed some promising results. It's really a state of the art convolutional neural network for image classification. All right, so coming back to where we started off, right, in this space. So we did see that neural networks have been around for a while. Possibly some of us heard about it before, but it really came to a point where, beyond the last few years, things have started picking up very, very rapidly, right? So the question that comes into mind is, what has changed? Why was it not like as popular as it is right now in 1943 when it was first introduced, right? So the answer is because we have made leaps and bounds of advancements in computational space, right? There is a very nice paper on phase transitions on massive computations by Professor David Donahoe from Stanford. He's a professor in the statistics department. He also teaches a class, by the way. I think you guys might find some of the online lectures. So he teaches a class, and he calls it massive computations done painlessly. And he talks about various state of the art ways of using some of the cloud computing techniques, some of the modern software developments that has happened in this space. So essentially, in his paper, and in the way that we are looking at things right now, is that there has been a paradigm shift in the way we do computations, and as a result of that, multiple things are starting to come together, right? We are trying to see some of these research that was done in the early days. Can we use the computational techniques to mine massive amount of data, big data, into all of these um, you know the same fundamental principles, really, the perceptron or the neuron concept, but just trying to take advantage of the modern computation techniques to make some of those things more practical in a way. And in his paper, Professor Donahoe, he talks about mobile revolution, right? So and he gives you different curves out of what's happening in the mobile revolution. So mobile phones really, like, and I can testify to that, although I'm not very old, I would like to claim, but I didn't have a mobile phone when I was a kid, right? I see my nephew now. He is like barely 1.5 year old. He already is playing with a mobile phone. I'm like, wow, I would never even imagine that, right? So we did see in our lifetime, some of our lifetimes, that there has been quite a bit of revolution in that space. And what is happening out of that is that we are generating a humongous amount of data, and really some of these graphs show you that we have a huge boom in the number of users, and as a result of using the smartphones, we are also generating a lot of data. And in fact, in his paper, he mentions that in every 60 seconds, you are generating 1,800 terabyte of data. That's combined all of us. So there has been quite a lot of data that's being generated, and as a result of generating this data, and companies that rely heavily on data driven analytics all throughout the world, they had to come up with this data centers that they have set up in different parts of the world, various exotic parts as well. It's these are massive rooms with just hard drives in them, and they compress the data, they pull all the data from around the globe, and they put them in the different data servers, or the data services room that they call them, right? So and in those rooms, they also have these different computational resources that actually try to make some sense of what the data that they are collecting. There are lots of caveats to that. There are things related to data privacy, data security, but if we don't go into those aspects, there has been definitely a huge improvement in the way we actually store the data and we make use of them, right? So and as a testimony to that, we can see that we have massive growth of data centers. In fact, we had a similar concept in geophysics before it really took over in the tech industry, right? We had massive data rooms from companies like, for example, Wesenjico. Like there were huge buildings storing seismic data, and it was a similar concept, right? But back then we didn't have a lot of the new computational resources that currently these companies have, or even in the oil and gas industry, we have some of these computational resources as well. All right, so as a result of that, we are relying on a lot of our decisions, especially a lot of our business decisions, on using this data and trying to explore some of these computational resources, and making sure that we use them for some of our decision making. And as a result of that, what came in were this computational resources companies, like, for example, to name one, Amazon, that had set up their computational centers, and they would put in a lot of these computational resources, and have like made them available to all the users through internet, right, through the cloud service. So we can now use some of their resources, which would actually cost us a lot of money if we had to maintain on our own, at some pennies. And it's really now the CPU hour, right? So based on your pay per usage kind of a term, so you can use the CPU, you can borrow the CPU and the GPU, and can pay as you require, and use those computational resources for your own benefits, right? So this was a huge thing. And like I mentioned, there has been a quite a bit of data, and we also saw that I'll not go into a lot of details of this, but I would share this slide back with you. So there are some interesting figures in here. For example, the gaming industry has come up really fast, and they came up with what we know right now as the graphical processing units for the games, because they needed number crunching to be done very fast for the rendering purposes, and we are starting to use some of those technologies for machine learning, right? And what GPUs actually give you as an added advantage over CPUs is that you can do the number crunching really fast, and this is what is shown in this graph here. So if you compare a GPU with some of these modern if you compare a CPU, sorry, with some of these modern GPUs, you can see that you can almost get a 50 times boost in the speed of some of these computations. And this is what is actually enabling some of these massive computational exercises that we have, right? So we have now seen that there are better ways of storing the data in the data rooms and all these data servers that we have. We have computations computational resources which are available to a lot of us through just by logging in. We have the GPUs, we have the CPUs, which really made the computation faster. And as all of these were developing, people like Google, Nvidia, Facebook, and others started developing what we know right now as the different packages for doing deep learning, right? So you really don't have to develop everything from scratch. You don't have to write a code to do all these weighted averaging that I just described. You can use some of these packages which are pre-built and have been made available to everybody as part of the open source collaborations by these companies. And you can just grab, for example, TensorFlow, which is from Google, to do some of your deep learning work. You can use Torch or PyTorch, which is the Python version of it, to do some of your machine learning kind of a workflow. So yeah, so that's another key development that happened in this space. And as a result of all of this, what happened was, we saw a huge number of research coming in uh, as a result of this. And in 2015, some of these key neural networks that were used for image classification problem actually outbeat us. It was better than human performance in the image classification space. So that was a big boost, right? And then we came to a point where the world champion for one of the games called AlphaGo um, was actually defeated by a machine that was based on some of these deep neural network and stuff like that. And yeah, we could see that there's a huge performance boost, and we are starting to outperform ourselves. So yeah, so this is where things got much more interesting. And to summarize all of that, I described like what we have what we call as the data, uh, a lot of data coming in, and we are storing them in the data rooms. We have the cloud computing technologies and the GPUs that came in. And finally, what it all led to is a whole new paradigm of doing research, right? Right now are lots of people in a lot of research institutes who are just looking at data and trying to make sense of the data using some of these techniques, and they are not really trying to look at developing a new physical law or a model that describes the data. So it's mostly trying to get the machines to do a lot of your work in that space. All right, so that was hopefully a good enough overview of how things evolved over the last few years, and how we are starting to use a lot of these data driven methods for our for our work, and why exactly we see a change in the way we are doing things. So another concept that came in, and this is a slide that I borrowed from Louis Lee. He's ex Stanford student. He did his PhD in Stanford, right now working in Chevron, and he describes it, in a very nice way. So I'm sure when Professor or Dr. Ranjit Shaw was describing his reservoir characterization, he must have talked about inversion, right? So we have the data, we try to invert for the model that describes the data and matches the data, right? So this is what happens. So you have the data, you have the model, you're making a prediction, and you're trying to minimize and find the parameters of this model where you can describe your data in the most appropriate way, right? But Lewis, when he did his research, and this is the whole field of Bayesian evidential learning. So Lewis is doing it, and also one of our ISM alum, Anshuman Pradhan, he's also working on this Bayesian evidential learning. um, what they describe is that instead of going through this whole route of getting the model and then doing the prediction, we can really skip this whole model part, and we can directly start predicting from the data, right? So there's no explicit inversion done for this. And this is what they call as evidential learning, right? Because this is based on evidence. So you have data for, like, all your past measurements, and then you start making predictions based on those evidences. And there are some details on that, and I'll leave it at this higher level. But there's a whole uh, range of work that's done for Bayesian evidential learning. And in this, actually, what they put a lot of emphasis on is to capture the prior knowledge. So if you can capture what is the prior in this data space, you can actually take that prior and narrow it down and call it a posterior based on what you observe, and then you start making predictions from there. Right. So, I mean, there's a whole Bayesian evidential literature around that. Jeff Kears, who is one of our professors in Stanford University, he has a book on that. You guys can probably look into that as well. I think there is an online version available. So that, I mean, if you guys are interested, you can definitely pursue that part as well. Now, when we come into machine learning and all of these data-driven methods, we see that most of these methods, if we do not do some some trick to them, they need what we call as the label data set. So, and what is a label data set? Label data set is something where you know both the input and the output, right? And remember, when I talked about the perceptron, the basic building block of the neural network, I said that you try to minimize for what you observe and what you predict, right? So which means that you need to have both your uh, the both for your input data set, you need to have what you are observing as an output, and then you should, as the base as a result of applying all this machine learning work, you should get a prediction as well, right? So you have the y observed and you have the y predicted, and you're trying to minimize the error between them. So that's what we call as the labeled training data, right? So where you need to have the input and the output. And if you make your network very deep, or if you have a lot of layers, which would mean that if you have a lot of trainable parameters, number of weights, if they are a lot of them that you need to optimize as part of your optimization function, you would need an equal, if not more, amount of data. So these methods overall need a lot of label data set. And there has been a lot of drive, not just in our industry, not just in geophysics, but in overall in the whole machine learning data science research world, where people are trying to circumvent this problem. So if you can really start making predictions from a few of these labels, or if you can really turn this whole supervised learning problems where you need the training data into an unsupervised problem, be it through physics, be it through some other stuff, then that really gives you a whole new power to do a lot of these data analytics on data where you probably do not have the labels corresponding to them, right? So there is a lot of research done on it, and yeah. So uh, just as a pointer, as a high level stuff, I did some work on that as well, and we tried to use the physics of seismic forward modeling to turn a supervised learning problem into unsupervised. So if you're interested in that, you should definitely check out some of my papers that got published, and some other people have also published after I published on the same lines. So yeah, so that's one of them. So talking about label data, and just to give you guys a very good feel of what label data is. So when in an image classification problem, for example, for Alexnet that I described before, you have different images, right? So these are your x's. So remember, in our perceptron example, we have all the x on the left hand side. So these are all your x, and you have the corresponding y. So which are the labels? So in this case, for example, this image is a cat, the other one is a dog. And what you do is that you start predicting based on your optimized weights, and your prediction is a new image category. So once you put a new image, you will either classify it as a cat or a dog. So in this case, the labels are the classifications as cat or dog, and the inputs are the different images, right? So all right. So in ImageNet, and I think also Alexnet adopted that, you have a lot of these training data sets. You have around 14 million labeled images, which is a huge amount of data, right? And you have around 22,000 classes of that. And that was how this massive deep neural network was trained for months at a scale to come up with the weights that can predict the image class for a new image that's not in this labeled images. So what about in geophysics and in geosciences, right? So we also have a lot of data. In our case, for example, we have a lot of seismic data, right? So in most of the fields that have been explored over the past, like forever, we are producing oil and gas. We do have at least a 2D or a 3D seismic data for that, right? And those each trace in that data in that seismic volume is actually a data. And if you think about it, those traces also come from all the data that are being collected. Like for example, in the receiver domain, for example, for each shot you have a set of receivers, and all those receivers, the response of those receiver, combined together forms that one trace. So we have a huge amount of data, right? But we do not have a lot of labels. And what would be a label in this case? A label would be some ground truth. For example, if we drill a well, and if we know exactly, for example, what is the lithology, what is the reservoir property, what is the fluid content in the reservoir, that would be our label. So we really do not have a lot of these wells drilled, right? So in an area where you're exploring, you would have, based on your type of the field and type of the reservoir and stuff like that, you would have uh, much smaller amount of well logs, because they are expensive as compared to the number of seismic traces, right? So really, that brings us to a challenging part of this, right? So we do need some domain knowledge to augment what we do in conventional machine learning. So we really cannot live with what the ad industry or the image classification problems had. So they have a lot of data and labels, but we do not. So probably in our domain, we should use physics and a lot of statistics or a lot of domain knowledge to actually make better predictions. And in fact, this is what happens, right? One doesn't simply dump raw data into a machine learning algorithm. It's really just not the raw data. You need to really think about the problem, make sure that you augment the data correctly to make sure you can actually optimize for the weights, right? So it's not as easy as it sounds sometimes. So all right. So having said that, machine learning is not actually a black box. So you can actually go inside the machine that you're training and try to make sense out of your domain knowledge. What is happening? What are the types of weights that's being optimized for? What are some of the internal layers of the model looking at? And that's where you do really need your domain knowledge and the domain specialists to come in and really think about the problem hard, right? It's not just dumping in data and getting prediction. That's not where the world is heading to. The real challenge is to do it more cleverly and not make a machine do like something without really understanding anything, right? So that's where some of these modern research is going on. I was just looking at my time. I think I might have to speed up a little bit. Right. So, okay. Well, this is a cartoon that I found very interesting, right? So what can humans really do better than machines? So right now I think that we are becoming a bottleneck in some of these problems, and yeah, if you get time you should read this. It's pretty funny. All right, so I'll give you a very quick example now of a deep learning method which was applied for a geoscience problem, and I think some of you might recall some of these slides, and this is from my work in PhD where I used convolutional neural networks for inversion problem, and in this case, what we had was so now I'll try to bring back some of these concepts that I've given you before. So in this case, the label data is the input normal seismic data, incident seismic data, which is what we call the post-stack seismic, and the corresponding output is stochastic impedance, right? So this is our label data set in this problem. And a basic workflow that really we follow for most of these machine learning problems is to first make sure that we have the right type of data. We have a If we are doing a supervised problem, we need the label data set. So once we have that, we try to design a network, we try to train it, and then try to test it on a development set. So that's where we try to optimize for what is called the hyperparameter, or the number of layers, the number of neurons, the number of the size of the neurons and stuff like that. We try to optimize for them, and once that is trained, we try to test it on a different set of data set that was not used for the training, right? So that's where we really try to see how good the machine is in making some predictions. And of course, after you do the prediction, that's actually where a lot of our work starts, right? Because you can really it's quite fast nowadays to design a network and start getting predictions, but the real important part of the problem remains on the performance evaluation. So when is the network predicting good, when is it failing, can we understand what is the basis for some of these predictions and stuffs like that, right? So that's really some very important stuffs in there. So you guys know about the label dataset now. So for this problem, like I said, our label dataset is seismic and its corresponding impedance, and both of them are known in this case. And that's what we are using for training the network. And once the network is trained, we will feed it in with data that's not known, right? In the interest of time, I'll not go into details of this, but I mean, like I said, we do not have a lot of wells, right? So we had to use some domain knowledge to really create some label data set. And I think I described it in quite a little bit of details when I was presenting back in January. But really what we did was we tried to use rock physics modeling, stochastic spatial modeling, and forward seismic modeling to really use domain knowledge to generate geologically realistic but synthetically generated training data set. All right, so yep. So once we had all the training data set, we tried to come up with a network. It's a pretty simple network, two layers of 1D convolutional neural networks connecting through a nonlinear activation, and then we tried to optimize for the weights using stochastic gradient method. In this case, it's called ADAM. It's pretty popular, and we tried to optimize for the weights. All right. So once we had the weights, now you can freeze the network. You can freeze the weights, and you do not need to train it again. Now you can put a input seismogram, which now we are predicting for. We do not know exactly what is the impedance for this, and now we use this weights to make a prediction, right? So that's what is really the business driver for using some of these techniques. So you like to train it on the data that you know, and then you would like to apply it for the rest of the field. I did a little bit of a comparison there, which is part of the performance analysis, right? We should not really start believing the results. We should try to look into more details of it. So one of it was a comparison with traditional inversion schemes that really helps us to identify what the neural network technique does better as compared to traditional techniques, or is it even performing at par with the conventional techniques, right? So what we found out, for example, in this case was that if we look at the predictions for the impedance from our CNN, which is the convolutional neural network, we see that we can capture a little bit of the high frequency elements in the prediction, and that really comes from the high dimensionality that and the bigger function space. Remember, that's where we were chasing all these methods for. So we are capturing a lot of this high frequencies based on that. But I mean, if we really do a data to data comparison, and in this case this was a supervised problem, remember, so we had a model to model comparison. So we had the impedance predicted, we had an impedance observed, so we were trying to minimize that error. So we do see that the impedance correlation in case of the CNN inversion is really high. It's around 95%, and that is exactly what we told the machine to do. We told it that you minimize the error in between what you're observing and what you're predicting. But in traditional inversions, that's not how it's formulated. In our traditional inversion, we actually try to minimize the error between the data observed and the data predicted, right? So, and if you look at that, in terms of seismic correlation for the prediction, the traditional inversion actually gave us much higher correlation as compared to CNN inversions. And these things made sense, right? I mean, I'm not saying that, it's good, it's bad, but we need to make sense of what the predictions are giving us, and all of this made real physical senses, and we did improve on some of these things. That's how we came up with the physics driven machine learning method, where we put in the optimization function, the data observed minus data predicted. So that was some of the basis of some of our future work. So yeah, so I'll quickly go on to the last part, which is answering the what do we get out of this. So I've given you why we are doing data analytics. I've shown you a lot of how, a lot of it really touching on higher level for a lot of these things, and then finally, what do we get out of this? We get faster results. Yeah, so some of these computational techniques really turns around the delivery time for some of these results. And also, this is a great platform for data integration. So previously in our problems, specifically geoscientific problems, it's really hard to incorporate different data because it's in different scales, has different physics involved in it and stuff like that. So but data analytics and all these platforms really help you to bring all of those data into one uh, broad scheme, and then start predicting things that are of common interest, right? And of course, subject to what the problem is at hand, we do see in some cases data analytics and machine learning, deep learning to surpass some of our human performances, right? So it's not just in AlphaGo; it's also in geosciences that we are seeing it's surpassing some of our interpretations. All right, so I have two one 1 minute to show a quick demo, and I would not do a lot of data analytics there, right? But I'd like to give you guys a pointer to what you can do with what is called the Google Collaboratory, right? So let me try to do this, and it's going to be fun, hopefully. So I'm hoping most of you guys have a Google Drive, right, where you put in a lot of your music and your pictures, right? But in addition to that, there is something new that has come in, which maybe some of you have noticed, maybe some of you have not. It's called Collab Notebooks, right? That actually enables you to log into some of these Google's machines through the cloud, and really it's available to everybody. Yeah, it's free of charge. There's no charge. uh, of course, if you do some sophisticated stuff, you will have some charges. But all right, so if you go into Google Collaboratory, or really if you do not have even Google Collaboratory, you can, I think, do it from the My Drive itself. But let me just go into Google. So here you can, what you can do is you can right click on here, and you can go into more, and you can go and create a Google Collaboratory notebook. So So I told you, right, there is a huge paradigm shift in computational resource and how things are allocated, right? So what you just did right now was unimaginable even 2 years back or 5 years back, right? So what you just did with that click is that you booked a resource in Google's high performance computing centers or wherever, with a huge amount of GPU, with a lot of pre-installed stuffs. And if you want, you can also get a GPU, right, which is pretty neat, I would say. So if you go into runtime in here and change the runtime type, you can actually get a GPU, or what is called a TPU, tensor processing unit, that Google has come up with. And you can get a runtime. So this what this runtime is basically you just bought or got hold of a computer, a pretty powerful one. Yeah. All right. So once you have that, what really enables a lot of us to do a lot of things is that everything is pre-set up for you. So if I say, for example, I don't know if you guys are aware of this, but a very powerful library in Python is called NumPy, right? So first of all, Python is installed in it, TensorFlow is installed in it, Keras is installed in it, PyTorch is installed in it. Woohoo! That was the first step. Like that's by the, like, one of the steps which drives people out of this whole world by itself. But everything is installed. So what you need to do is, like, for example, if you guys are Python coders, you will know that you can import NumPy as NumPy array, and you can also import something like matplotlib, which is a plotting library uh, for plotting some of these stuffs. And what you need to do is just to execute the cell, and that should do your work, right? So cell is already running. What happened? uh, Matplotlib. This is the fun part of doing a live demo. But yeah, let me check actually. Okay, yep, there you go. Yep. So everything is imported. So the plotting library is imported. The NumPy, which is an equivalent of MATLAB, is imported. And now you can start doing crazy stuff. So I'll just make an array, right? Let me just put in 3 numbers, and I'll make another array. Yeah, so I'm not teaching you programming here. I'm just showing you, how easy it is actually to get started everything. So these 2 arrays can be your, for example, seismic data and impedance. And basic data analytics is just doing cross plots, right? So that's really where everything started off. So what you can do here, and I hope it works. Hooray. So we have our plot. So that's where it begins, the data analytics stuff. And you can do a lot of fancy stuffs in there. So all of your Python programming and everything can be done here. So I'll leave it at that. And yeah, hopefully I can stay a few minutes or like after our stipulated time. So, but I'm happy to take some questions and comments.
So thank you very much, sir. That's really a good outline. One who want to pursue machine learning or AI-related geoscience, or who is already pursuing this. So now I'd like to request Abhishek sir for today's vote of thanks session. Please notes over to you.
Sure, Madhumita. Thank you very much. And again, Vishal, thank you very much for the presentation and for the Q&A, which I guess was fantastic, getting some kind of feedback, observation from everyone, including some of the other speakers as well. So I would like to take this opportunity now that we draw to a conclusion of our webinar series. 9 presentations, 7 speakers across a span of 7 days. This wouldn't have been possible without the platform that the Geophysical Society, which each of us by default are a member of, providing us this platform. So I would like to thank the society itself, its patrons, current patrons, for giving us the opportunity. I would like to thank Dr. Shaw, Pragajyoti Mojumdar, Partho, Shubhro, Orpana, and Vishal, most of whom are in this call, other than Pragada and Orpana, for honestly the kind of time that you devoted, your passion for the subject as well as for the students came out through your presentations, how you took the questions and just set the bar really high if we have to do this ever again. So thank you so much. I must appreciate. I know every student has had some role to play, and just by taking a few names, I don't want to lessen the credit of the others, but certainly the ones who have had to bear the brunt of a lot of questions from my end, WhatsApp, texts, emails over the last 2 weeks, Prithijit, Ishika, Madhumita, and Shundip. Thank you very much for being there, because I have been demanding at times, and every time you have certainly stepped up. I would, last but not the least, want to thank every one of you attendees, be it students, research scholars, faculty members. I hope you have gained something out of each of these sessions which were presented to you, and you have also overall understood uh, the motive behind conducting these sessions. It is one thing to talk about things in flowery words, and the other thing is to actually do it and demonstrate that this was an exercise which helps everyone who participates. The likes of us, certainly, through the discussions as well as the questions that come our way after presenting. And I'm sure the students also gain a lot of insight into what's going on in the area of research and in the area of advanced workflows in the workplace. So overall, thank you very much for your attendance and for participating and making this a success which we would like to replicate in the future. There is also something which I'm not committing to at the moment because these are still initial days. We would like to close this out properly. There is a feedback form for most of the attendees that would come out from the organizer. It roughly takes about a minute or so to fill it up. Please do so. That would only help us get better for organizing such things in the future. That's one thing. The second thing is, these lectures were all subject specific. We understand that there are many things which are more career oriented and subject oriented, not necessarily following a particular bracket or subject. We are trying to plan a more informal session where we would like to get again both sets of people, some alumni who are in the industry and the students, and have an informal discussion. Obviously, time zones and time of the day and work day versus weekend, we need to sort out all the logistics, but there should be something coming your way in the next 5 to 10 days, depending upon how quickly we can organize this. So that's all I had. Over to you, Madhumita, to conclude the evening.
Yes, sir. Thank you very much. Thank you very much once again to Abhishek sir for helping us to organize this webinar. And thanks to all the attendees. Hope all of you enjoyed this one journey. And once again, I am reminding you all that please fill up the feedback form, send to your email. So now I think it's time to leave. Okay, thank you.